All right, today we're just going to finish up the redox, chapter 5, and then we're going to talk a little bit about Lewis acid-base reactions, and then go on to chapter 6. So let's take a look at one of these reactions I want to do. Let's continue our discussion of skeleton redox. All right, one thing that you notice when you're doing skeleton redox is the right side of the equation. Let's start to record this. Yes. Keep this over here. Looking at the right side of the equation, the products are given, or at least the major products are given. So for example, chlorine with bromide gives chloride and bromine. And so you don't have to determine what the products are. The major products are given here, here, here. And so the situation with skeleton redox is we just have to complete the equation, that is, just balance it. And the reason we have skeleton redox reactions like this is because often it's difficult to predict theoretically, the right product. For example, how do you know when you burn something you get all CO2 and no carbon monoxide? Is carbon monoxide a potential product? Yeah, when you burn something, you could form carbon monoxide depending on the conditions. And so if you change the conditions a little bit, you could change what products you might generate. And so under certain conditions, carbon monoxide is favored. Under other conditions, carbon dioxide is favored as a product. And so tell me when carbon monoxide is favored as a product. Can you pinpoint it exactly? Theoretically, that's kind of difficult to do, right? You can do it. You can spend years figuring it out, but is it really worth it? No. What you do is you just add plenty of excess oxygen to minimize the production of carbon monoxide. And so this is the same thing with chemical reactions. You want to spend years of time researching and using theory to figure out exactly what you're going to produce under these conditions. Not really. What you will typically do, because the theory is complicated, what you'll typically do is just mix it together and see what happens. Hopefully you don't get an explosion, right? And so you just carefully mix it, see what happens. Carefully mix it, see what happens. This is called, there are two I talked about the two-pronged approach. Do you remember that? Does anybody remember? Tell me what the two-pronged approach is to chemistry. Theory and experimentation. And so the two-pronged approach happens in science all the time. You have your theoretical people on the computer, and then you have your experimental people working in the lab and mixing things up and trying to get things. Well, right now, a lot of chemistry is not theoretical. A lot of chemistry is just experimental. Mix it, see what happens. And so if you go to certain labs, what you'll see is these microreactors. In the microreactors, they can do 1,000 different combinations all at once. And so each microreactor has a little, like 1,000 little tiny cups, and then they mix different ratios and different conditions in those. And so in one shot, they can determine, how that impacts, how the different conditions impact what product you form. For example, in the search for, the two-pronged approach is, there's a great story about the search for the green LED. Have you heard of that there? The search for the green LED. So you had a whole bunch of theoreticians trying to figure out what is the optimum composition to give a green LED. The green LED was the holy grail of LEDs because they had red LEDs, they had blue LEDs, but what they were missing were green LEDs. Without a green LED, you couldn't make all colors of the rainbow. And so this was a huge push by theoretical chemists and experimental chemists to get it. And do you know who got it? An experimental chemist got it. He was the first to the green LED. And so a pretty interesting story. Actually, that green LED made billions upon billions of dollars, and he got a $5,000 bonus or something for developing the green LED. He ended up suing his former employer for that. It was I think maybe 5,000 was an over-exaggeration. Maybe it was less like $1,000 bonus for that. And he actually won. Yeah, I mean, he did all the developmental work himself. He's actually a professor at UCSB, so that's why the green LED story is pretty big there. But anyway, getting back to this, so sometimes you just mix it and see what happens. And so that's what you do. You mix it, see what happens, analyze for the major products. So these are the major products of these. And you can see all these are skeleton-type redox in which the major products are given. So we can do a lot of prediction. For example, when I predict, for example, if I were to burn methane, what are the major products you predict from the combustion of methane? Carbon dioxide and water, right? Under normal conditions, CO2 and water. What if I spray ammonia in there? What I would predict is, if I add ammonia is electron-rich, electron-poor? Electron-rich, it should burn as well. And what I typically expect if I add ammonia into the mix is I expect NOx. You know what NOx are? Oxides of nitrogen. Things like nitrous oxide, nitrogen monoxide, nitrogen dioxide, those are NOx. So you'd expect to burn the ammonia to NOx. However, we saw this in reaction chapter 4. Here, when they decided to burn the methane and oxygen, they added some ammonia, but they didn't get NOx. What did they get? In fact, they didn't even get CO2. Under these conditions, and I don't know what the conditions are, but under a certain set of conditions, they got hydrogen cyanide gas and water. I'm sure under vigorous combustion conditions, with high temperatures, hydrogen cyanide wouldn't last. That would be burned to CO2 and NOx, right? But under maybe these are mild conditions, not much oxygen, then what do we get? And so you aren't going to spend years figuring it out, or months or days figuring this out. You just try it and see what you get. And so this is a reaction that makes you think twice. You got to watch out because you could get hydrogen cyanide. What do you know about that?
Yes.
It's a gas, and
Yes.
I guess it has a taste of bitter almonds. But you never want to taste this stuff because
It's toxic.
yeah, it's so deadly. It's extremely toxic. And so you got to watch out because some things sometimes because of the conditions, and chemistry is complicated. It's complex. It's not always straightforward. You get products that are unanticipated. And this would be a product that's unanticipated. And so anyway, let's try to figure out what happened in this particular reaction. So for this skeleton redox, number 46A, we have methane and some ammonia and some O2. All these are gases here. And this produced some hydrogen cyanide and gaseous water, H2O gas. I'm going to put the states because these are all non-aqueous. All right, so what's happening in this particular reaction? Well, in skeleton redox, we get a much clearer picture of what's happening in this particular reaction. And so what's the first step in skeleton redox? We want to separate it into half reactions. And so we should get an oxidation and reduction half reaction, but we don't have to pay particular attention to which is which. We just do it. The way we separate it into half reactions is we just take methane. Where does all the carbon in methane end up? In hydrogen cyanide. So we know that methane has to go to hydrogen cyanide because, atoms are neither created nor destroyed. And so that's what happens. What about ammonia? Where do all the nitrogen atoms go in ammonia? Into hydrogen cyanide too. So methane and ammonia yield hydrogen cyanide. Otherwise, the atoms are wrong. Now, what about the hydrogens? The hydrogens we don't care about. Hydrogen and oxygen, those are balanced using our process here. And so I'm not concerned about the hydrogens. All right, now, what about the oxygen? Where do the oxygen atoms in O2 end up?
Water.
In water. All right. Sometimes what we can do with the skeleton redox is we can save ourselves some time, by familiarizing ourselves with the table. Have you ever seen O2 go to water? O2 go to water in a redox? Yeah. Yeah, I saw it right here. O2 goes to water. And so rather than following all the steps, I'm just going to copy this down. O2 gas plus 4H plus AQ plus 4 electrons yields 2 H2O liquids. And so I'll save time this way. O2 gas plus 4H plus 4 electrons yields 2 H2O liquids. Something like that. Now this is gas, so it's not perfect, but it's all right because we just got to do the best we can do. Now to convert liquid to gas is easy. You just raise the temperature, right? And so that's not a complicated process to do. Do you see that? Just save time and then write it. But do I have methane and ammonia on my chart? Can I just copy down the half reaction from there? No, I already know it because I know the chart. And how do you know the chart? How do you guys know the chart?
Read it.
You read it. You won't believe how many people don't read charts. And the reason, actually yesterday, this came out because some people noticed, why is water at the bottom? Water is not at the bottom, It's because there are two charts in there. And it's two charts. When do you want to learn about the two charts? And when do you want to learn about water? And when you want to learn how to use that chart because it's different than this chart here. The night before the test, when there's a lot more pressure, or well before? Yeah, well before. So whatever you do, when you have a new chart, just read it from top to bottom, bottom to top, just to familiarize yourself with the chart. Doing little things like that can prove critical on timed exams. Our exams aren't really strictly timed, but at UCLA they were strictly timed. And if it takes you a long time to search the chart to find what you're looking for, that's time wasted. Time wasted that you could have saved if you were more familiar with the chart. And so those are little tips for increasing your speed. Well, anyway, what we do here is a process. We're going to either balance the carbon and the nitrogens. It doesn't matter. We'll start with the carbons. And so we have one carbon here, one carbon here. So that's checked. That's balanced. The nitrogens, let's balance those. We have one nitrogen here, one nitrogen here. It's already balanced. So we balance all elements other than hydrogen or oxygen. And then what? We balance out the oxygens, but there's 0 oxygens here, there's 0 oxygens here, so it's already balanced. Check. And then what? We balance the hydrogens. So that's 7 hydrogens here, 1 hydrogen here. They're not balanced. So how do you balance hydrogen? By adding H+. So we're going to add 6 H pluses over here. And then we balance out the charge. So over here it's 0 plus 0 gives me 0 charge. 0 plus 6 gives me plus 6 charge. And how do we balance out the charge?
Plus 6 electrons.
Yeah, plus 6 electrons up here, so plus 6 electrons, and we're done. And so these are our two half reactions. Now, how do you check a half reaction? It's simple. You check a half reaction by making sure the atom's balanced and the charge is balanced. And so let's see, the earlier you catch mistakes, the better, because then it's less work redoing things. And so 1 carbon, 4 plus 3 is 7 hydrogens, 1 nitrogen, 1 nitrogen. So the atoms are balanced. Then we check the charge. 0, 0 equals 0. 0 plus 6 minus 6 equals 0. And so 0 and 0. This is what we call a balanced half reaction. Now the balanced half reaction gives us insight into what's happening here. For example, methane and ammonia, this pair is called the what? That pair is called the reducing agent or the oxidizing agent? The RA or the OA? This should be automatic. This produces electrons. If this produces electrons, it's the RA, right? This pair does what? This pair going backwards does what? Consumes the electrons. It does not. It consumes the electrons. It does oxidize something, but it consumes the electrons, so it's the
Oxidation.
yeah. This is the conjugate relationship, right? RA-OA conjugate relationship. This pair does what? This species does what? Yeah. And so what we'll do is we'll just analyze this later. The easiest place to see the RA and the OAs is in the half reactions. Because when you look at the net reaction, take a look at the net reaction. Is it easy to tell? With a net reaction, it's more difficult. You can still tell, but what you have to do is you have to write out all the oxidation states in order to see what's happening. But when you do it in half reactions, it's simple to label. Yeah.
Why weren't you worried about the hydrogen going to the water or the net equation? And writing the half reactions?
Why wasn't I worried about the hydrogen going? Because hydrogen, will balance out at the end. You don't really have to worry about it because if the hydrogens aren't balanced, you're going to add them anyway as H+. And so the same thing with oxygens. If the oxygens aren't balanced, you're going to balance it by adding water. And so we don't worry about hydrogen and oxygen. These steps aren't the theoretical way these react. These steps are just a simple way to figure out what's the net reaction, the balanced net reaction. Do we really add the hydrogens? When you look at this, is there an AQ? You see any water present? Gas. This is steam. This is not liquid water. You see any AQs? No. So what am I doing with H plus AQ? Well, I don't care because this is just a process for figuring out the balance, how to balance this. And so I'm not going to worry about it right now. We'll do another example. All right, the next step is we need to add these up, but when I try to add them up, I notice that there's 6 electrons produced, but only 4 electrons consumed. And so it's not balanced. We have to balance it. How are we going to balance it? Yeah. So we'll go 4, 4, 4, 24, and then 24. And then 6. Actually, no, I'm not going to do 12. Yeah, maybe 12 would be better. Sorry. looked at that. Let's do two, this will save us some work later. 2, 2, 2, 12, 12. And this will be 3, 3, 12, 12, 6. All right, then to save myself some time, I'm just going to go ahead and cancel the things, that appear on both sides of the equation. That is, I have 12H pluses on the right side and 12H pluses on the left side, so let's cancel those out. And then I have 12 electrons on the right side, 12 electrons on the left side. We're going to cancel those out. Anything else I can cancel? No. And so, rewriting this, now I'm going to get 2 methanes plus 2 ammonia plus 3 O2 yields 2 HCN plus 6 H2O. Now, H2O is a liquid here, but I'm just going to convert everything to a gas. It's at high temperature, so the liquid would have been converted into a gas. Anyway. If we convert the liquid into a gas, it changes these. Because remember, what did I say the concentrations were for our reactions that we're predicting? Does anybody remember what the concentrations were that we're assuming? 1 molar. Good. And also, the other thing we have to assume is the temperature. The temperature is at 25, but we can make some changes, and it's going to impact things, but sometimes it still works out the way you expect. All right, so let's see. This is our net redox reaction. Let's just check if it's balanced. 2 carbons, 2 carbons, 8 plus 6 is 14 hydrogens, 2 plus 12 is 14 hydrogens, 6 oxygens, 6 oxygens, 0, 0, 0, 0, 0, 0, 0, so it's balanced. So this is it. And then what we want to do is we just want to do a quick analysis here of the driving force for this. This is the RA, this is the OA, this HCN is what? This is the OA, and H2O would be the RA. HCN, normally when I think of HCN, I think of it as being a reducing agent. It's a really good reducing agent, but it could go either way. And if we went backwards here, it would be actually the oxidizing agent. So looking at this, the reason I think of HCN as a reducing agent is because you can burn HCN. And just combust it. So are we going, is there a driving force for this? Are we going stronger to weaker? What do you think? Yes. This reaction occurs. How do I know this reaction occurs? How do you know that there's a driving force for this reaction? Because they told us. They mixed these together and saw what happened. They mixed them together, what happened? They got a reaction. What did they form? HCN and steam. And so they mix it and determine. And they just analyze it using some kind of instrument or whatever, figure out what form. And so this would be an example of a skeleton redox. We do have a driving force. All skeleton redoxes have a driving force because all of them occur. This procedure is the same as Chem 4. This is no different, right? In Chem 4. And in fact, in Chem 4, they had things very similar to this. What is going to be different is we're going to add one more thing to the Chem 4 procedure. and that is this. When you do these reactions in solution, you have a choice here. You can adjust the pH of the solution. So we can balance these equations in acidic solution, meaning the solution is acidic with some acid present. Or we can balance these equations for basic solution. There's actually one more choice. We can have acidic, basic, or neutral. If we have a neutral solution, then it's the same procedure as acidic solution. All right. The reason we have to split it like this is because the way we balance hydrogen. How do we balance hydrogen? By adding H+. H+ is strong acid. Is strong acid stable in basic solutions? No, it's not stable. And so we don't want to have two different procedures, one for acidic solution, one for basic. So what we're going to do is we're going to use the procedure for acidic solutions, and then at the end, we're going to correct it here. Because since H+ is not stable in base, we're going to change that. And so the exact same procedure, except getting rid of the H+. And I'll show you how to get rid of the H+. Here. And so let's take a look at the book's problem here. This is one of the advanced ones. We'll do 78C. 78C, CRI3. What's CRI3 called? Chromium 3 iodide plus H2O2. H2O2 is hydrogen peroxide, yields CrO4 2-. That's chromate plus IO4-. Not iodate. Periodate. And so we're given the skeleton reaction. They just mix some chromium 3 iodide with hydrogen peroxide. You mix that together and then you analyze the products that are formed. And so they got some chromate, which is yellow, and some periodate. These are the major products. But this equation certainly isn't balanced. Let's figure out what's going on in this redox reaction by doing the skeleton redox method. So the skeleton redox method is just this. It's CRI3 must go to what? Where do the chromiums end up? In chromate. Where do the iodines end up? It's got to end up in periodate. And so what we have here is the chromium 3 iodide gets converted into chromate and periodate. Do we care about the oxygen? No, oxygen and hydrogen we ignore. All right, then that leaves hydrogen peroxide here. Where does hydrogen peroxide end up? In the chromate? In the periodate? Neither. The hydrogen peroxide, where it ends up, it doesn't matter because it's hydrogen and oxygen, and we will take care of that in the balance procedure. So we don't really care. All right, so let's go ahead and start the balancing procedure. We'll start off with chromium. One chromium on the left, one chromium on the right. It's done. And then we'll go to iodine. 3 iodines on the left, 1 iodine on the right. And so what do we need to do? We need to make this I3O4? No. We'll just change the coefficient to 3. Now we have 3 iodines. And then we go to oxygen. 0 oxygens. 3 times 4 is 12 oxygens. And so we will...
Add 12 waters.
Yeah. Add 12 waters. 12 H2O.
16.
Yeah, and then we have 12 times 2 is 24 hydrogens.
16. You forgot the O in the chromium.
Chromium.
That's right. 16 oxygens, thanks. And so we'll need 16 waters. Okay, so that gives us 32 hydrogens. On the left, how many on the right? 0, so we need to add 32 H pluses. All right, let's look at the charge next. We have 0 plus 0 gives me 0, and then minus 2, minus 5, plus 32 gives me plus 27. So how do I balance out the charge? Yes. Plus 27 electrons. And then we're done. So let's do a quick double check. 32 hydrogens, 16 oxygens, so that's 4 plus 12 is 16 oxygens. 1 chromium, 3 iodines, 3 iodines. Atoms are balanced. Then check the charge. 0 plus 0 is 0. Minus 2 plus minus 3 is minus 5. Minus 5 plus 32 is plus 27. Plus 27 minus 27 is 0. And so we're balanced. So this half reaction is good. When we look at a half reaction, let's go ahead and analyze it really quick for OARA. What is H2O and chromium 3 iodide combo? What's that? Or RA or OA? RA is correct. What is chromate peridate H plus? This is our OA. OA consumes the electrons. And so now we have the conjugates there. All right, now let's go over to hydrogen peroxide and let's balance this. We have 2 oxygens on the left, 0 oxygens on the right, and so we need to add, actually I'm going to do this in black, plus 2 H2O. This gives us 2 hydrogens on the left, 4 hydrogens on the right, and so I need
2 hydrogens.
2 H pluses. And then let's look at the charge. A plus 2 and 0. So I need 2 electrons. And so I have 2 H pluses, hydrogen peroxide plus 2 electrons yields 2 waters. Have you seen that before? Yeah, on the chart. There it is. Hydrogen peroxide, 2 H pluses, 2 electrons yield 2 waters. And so is actually the chart. Now what do we do? Let me erase these. Let's look at hydrogen peroxide and H plus. Hydrogen peroxide and H plus will be our OA, and water will be our RA. So here we have 27 electrons. Here we have 2 electrons. So what should I do to balance out the electrons? I'm going to multiply by 2. And so I'll get 32 waters, 2 chromium 3 iodides, 2 chromates, 6 peridates, 64 protons or H pluses, 54 electrons. All right, over here I'm going to multiply by 27. And so this is going to give me 54 protons. Maybe I should rewrite this. Maybe I'm missing. So you have 54 H pluses plus 27 H2O2s plus 54 electrons yields 54 H2O. Okay, so let's go ahead and analyze this. H plus and H2O2 we call the OA. H2O, all right. So this is what's happening. Now let's go ahead and cancel out. So I got 54 electrons on the right and 54 electrons on the left. So let's get rid of those. Let's take a look at the H pluses. I have 54 H pluses on the left and 64 on the right. And so let's cancel that out and make that a 10. There. What else? The waters. I have 32 waters on the left, so we can get rid of all those. And make this 22. All right, now we can combine. And so when we combine it, it's going to be 2Cri3 plus 27 H2O2s. I'm sorry? Okay, is that it? Yeah, looks like it. This goes to 2CrO4 2 minus plus 6IO4 minus plus 10 H plus 22 H2O. I'll put in the states later. We don't have to put the states in until the end. All right, the only time I have to worry about basic solution is when I get H plus as a reactant or H plus as a product. Here I have H plus as a product. Is that H plus going to be stable in base, strong acid? No. And so what's going to happen is, if this is in basic solution, I have plenty of hydroxide. And what I'm going to do is, 10 hydroxides, no problem. I'll just add 10 hydroxides over here. I have more, as many as I want, because it's basic solution. And so if I had 50 H pluses, I'd just add 50 hydroxides. If I had 100 H pluses, 100 hydroxides. Any amount is fine. This is base. All right, the hydroxide in the basic solution will react with the H plus to form what? Water. And so I'll end up with 10 H2Os. But the problem is if I add 10 hydroxides to the right side, is my atom balance still intact? No, I just screwed up my atom balance. Is my charge balance still intact? No, I screwed up my charge balance. So I screwed up both my atom balance and my charge balance by adding 10 hydroxides. The way to prevent this is to add 10 hydroxides to the reactant side. So we add 10 hydroxides to both sides so we don't screw up the charge and atom balance. And so the net reaction now is going to be 2 CrI3s plus 27 H2O2 plus 10 hydroxides yields 2 CrO4 2 minus plus 6 IO4 minus plus 10. Well, I have 10 waters here and 22 waters here, so let's go ahead and combine those. That gives us 32 waters altogether. Waters and liquids. All right, let's check the atom balance. 2 chromiums, 6 iodines, 54, 64 hydrogens, 54 plus 10, 64 oxygens. So this 8 plus 24 is 32. 32 plus 32 is 64 oxygens. So the oxygen atoms are all balanced. the net charge, this is 0, 0, minus 10, gives us minus 10 on the left. Minus 4 plus minus 6 is minus 10. So minus 10, minus 10. So we're good. All right, now what we need to do is we need to do this. CRI3 was what? Or RA. Hydrogen peroxide was our OA. Chromate and peridate OA. And water. All right. So we're going from stronger to weaker. And so this gives us some perspective. For example, hydrogen peroxide is a better oxidizer than chromate and peridate mix. And chromium 3 iodide is a better reducer than water. Water, do you expect to be a very good reducing agent? No. Somebody was asking me about chloride this morning. What do you think about chloride? Is chloride a pretty good reducing agent?
Compared to water.
And chloride and water, which is better? Well, when we look at the chart, chloride is here. Water is
But chloride is an exception?
here. So looking at the chart, it looks like what's better, water or chloride? Looks like water. Water is better than chloride.
But
That means chloride is more stable than water, right? Isn't that what that means? That means chloride is less reactive than water, more stable than water.
we know that's not true.
But yeah, it is the exception. The exception is chloride is going to beat water, but just slightly. And so chloride ends up being slightly better than water, but they're both unreactive. Do you think water is a very good reducing agent? Do you think chloride is a very good reducing agent? No, so neither of them are very reactive. Both of them are exceptionally stable. It's just that the chloride, based on the exception you learned, is going to be a little bit better. Doesn't mean it's good. It's just a little bit better than water, i.e. it'll react before water reacts. That's what I mean by better. So we get some perspective on things when we do this last bit of analysis, which you probably didn't do in Chem 4, but you wanted to in Chem 1. All right, so it's just this final step that we do for basic solutions. For neutral solutions, you just leave it as is and do the same things you do for acidic solutions. Speaking of acids, bases, we've pretty much covered all the reaction types: metathesis, acid-base, and redox. But is there a reaction type that we missed? It has to do with acid-base. We only covered one type of acid-base. Yeah, we missed Lewis. We didn't talk about Lewis at all. And so, at the end of chapter 5, this is when I want to talk a little bit about Lewis acid bases. The bulk of the Lewis acid base talk will come later after we talk about Lewis structures. And so this is just a brief introduction to Lewis acids and Lewis bases. Tell me some chemical properties of CO2. Is CO2 a pretty good metathesis ion? Does the CO2 participate in ion combination? No. How about, what else did we look at?
It doesn't burn.
It doesn't burn, right? CO2 doesn't burn. Burn is electron rich. CO2 we would consider as electron poor because CO2 has a +4 charge on the carbon. A +4 charge on the carbon typically means it's quite electron poor, you know? +4 is a high positive charge. So how poor is CO2? Very poor. So CO2 would be a good, powerful reducer or good, powerful oxidizer? Yeah, if you look at the number +4, you would think of it as a good, powerful oxidizer like oxygen, for example. You know, oxygen is a nice, powerful oxidizer as well. But there's a problem because they use CO2 in fire extinguishers. Do you think they would put oxygen, O2 gas in a fire extinguisher? Would it, yeah, why not? Because if CO2 is used as a fire extinguisher, then O2, oxygen gas, should do the same thing because they're both powerful oxidizers. Is that right? No. No. I mean, if you put O2 in a fire extinguisher, what are you going to do? You're going to fan the flames. You're going to feed the fire. Have you heard of that? These terms? Basically, you're going to get the O2 in there so it burns more rapidly and completely. And so why doesn't CO2 do the same thing? In fact, they use CO2 in fire extinguishers. They'd never use O2 in a fire extinguisher. It's just going to make your life miserable. But both should be oxidizers, right? It turns out that CO2 is not a powerful oxidizer. CO2 is a weak, it's not a reducer. CO2 is not a reducer at all. It's not one of those ones that are amphoteric that can go both ways. CO2 only goes one way, and that way is oxidizer. But its oxidizing ability is very weak. This is why they can use it in fire extinguishers, except for what type of fire? They can use it in oil fires, except for metal fires. What's the problem with metal fires? Well, you should know, metals are all electron rich. Look at all these guys, all the powerful, what do we call these? Reducers are all metals. And so in order to get CO2 to react as an oxidizer, you need a powerful reducer like a metal. Otherwise, if it's not a powerful reducer, it's not going to do much because CO2 is very unreactive. Right? You've never ranked CO2 up there with fluorine, with oxygen, with chlorine. You know, it just doesn't belong up there. And so this is what I call the factual knowledge because, you know, numbers don't tell you the whole story, right? You need to be able to put some kind of perspective on the numbers. This is why I always say this because, you know, I have friends that are looking for work too, and a lot of jobs are being outsourced. A lot of jobs are just being replaced by, you know, people who don't have to have much technical knowledge because all they do is they can just look at the number and tell you, the number says this, the number says that, right? But these types of numbers aren't like that, you know. These types of numbers require some memorization, doesn't it? But you think, memorization? What good's memorization? Anybody can do that. Well, you'd be surprised. A lot of people don't have much information memorized, and so they can't give you any kind of perspective on what the numbers mean. Right? And so this is why we need to memorize certain bits of information, otherwise we cannot put things into perspective. You know, if somebody asks you how powerful of an oxidizer is fluorine, can you tell them? You know? Well, it's at the top of the chart, it's the most powerful, but what does that mean? You know, you have to be able to put it into some kind of perspective, otherwise, you know, think about, if you can't put that into perspective, what good are you, you know, when somebody can just look it up? Well, and actually they can look it up anyway, but And so, getting back to this is the same thing with CO2. When you see +4 in certain other atoms and other compounds, that's nasty. This is violent, right? For example, if you saw chlorine with a +4, watch out. You're going to have a violent reaction. But a carbon and a +4, no big deal. We see it all the time. CO2 carbonate, is carbonate very reactive? Is carbonate a powerful oxidizer? No, but carbonate has a +4 charge on that carbon. No big deal. The chlorofluorocarbons, have you heard of the chlorofluorocarbons? Chlorofluorocarbons used to be used in refrigerants, right? And they thought the chlorofluorocarbons are the next greatest thing because they had certain thermodynamic properties which made them excellent coolants, right? And they were inert. They were inert, meaning that they weren't toxic. These were not, the only way you could die from this is by asphyxiating yourself. So the chlorofluorocarbons were very unreactive. Well, if chlorofluorocarbons are very unreactive, what's the oxidation state of carbon in this? +4. What does that tell you? And so, this is the type of stuff you got to memorize, little bits here and there, so you can understand chemistry. Because I'll tell you, the theory, like predicting a lot of these skeleton redox isn't so easy. And so there's a big need for people who understand things at a different level than just a rudimentary level. And it's as simple as just memorizing little facts here and there. Is that genius? No. That's not genius at all. But a lot of people think they're geniuses, these people who know lots of little facts like this. They go to the talks. Wow, that person knows so much, right? They must be a genius. No. Well, anyway, getting back to this, CO2 is, one of the chemical properties that you'll learn is that this is a Lewis acid. It's not a Bronsted acid because it's not a proton donor. It doesn't even have a hydrogen, right? But it is an acid. And so how does CO2 act like an acid? Well, what is a Lewis acid? The Lewis acid is a electron pair acceptor or electron pair donor?
Electron pair donor.
No. One more chance. Electron pair acceptor or donor?
Donor.
Unfortunately, you failed. Okay. No, it's a acceptor. So who's going to accept? Which of these three atoms will accept an electron pair? And so let's analyze this. One way we're going to analyze this is based on what do you know to do with these Lewis structures right now? You know how to determine the oxidation states. Let's go ahead and do that. Oxygen, carbon, oxygen. So we know that. So which one of these do you think is most likely to accept an electron pair? Carbon. An electron pair is negatively charged, right? And so what's positively charged? Carbon. In fact, acid-base chemistry is like this. H plus is positive, the bases are all negative. So acid-base reactions are positive and negative. Same thing, Lewis acid-base, positive and negative, but it's just we aren't looking at the positive that's coming from H plus. That's the only difference. The positive is coming from this. Well, let's take a Lewis base. A Lewis base, we'll just use water. That's an example. Water is a Lewis base because it has two electron pairs, and one of those can be donated. And so when we visualize what's happening with the Lewis acid-base reaction, here's our Lewis acid, here's our Lewis base. What do you think is going to donate? Well, the only thing that can donate is oxygen. What's the oxidation state of oxygen? -2. So imagine this. Imagine there's a collision here the oxygen collides with the carbon, a lone pair is there. Now, if the lone pair gets pushed into the carbon, there's too many electrons around carbon, right? Carbon, the max is 8 electrons, an octet. Carbon cannot expand its octet. Have you heard of expanded octets? So we cannot go beyond the 8 electrons. So what that does is, if these electrons get pushed into carbon, 2 electrons have to get kicked out to make room. And so what we'll do is we'll kick out this pair of electrons and put them on oxygen, so that we don't exceed an octet. All right, when that happens, we form this. That lone pair that was on oxygen is now converted into a bonding pair. The bonding pair that was on this bond here gets converted into lone pair here, and we end up with this. All right, take a look at the structure, that Lewis structure. Does it look good to you? Okay, why not? Why does that Lewis structure look bad? I see a lot of no's. Why does that Lewis structure look bad to you? Just explain it to me.
It's unstable.
Why is it unstable?
Because, let's say, it's more about carbonic acid.
Well, that's not carbonic acid. Well, maybe it is. You're right. H2CO3. Oh, that must be the structure of carbonic acid. H2CO3. 2 hydrogens, 1 carbon, 3 oxygens. Carbonic acid? Yes?
No, it's still unstable.
What makes it unstable? Normally when we look at Lewis structures, we look for an octet. Is there an octet? Yes, there is an octet. An octet means 8 electrons around oxygen. Octet, 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 duet, duet. Good. Everything's good. Everything has an octet, we're done. This is carbonic acid, yes? What's wrong with it then? You tell me specifically what's wrong with this Lewis structure. Oxygen wants to take the carbon? I don't know. I mean, isn't carbonic acid H2CO3? And so if oxygen takes the carbon away, then I'll have carbon monoxide and something else.
The oxygen prefers 6. Does the oxygen prefer 6?
Oxygen prefers 6 what?
Valence electrons.
This has 6. Oh, this has more. This has... Let's look at the oxidation state. What's the oxidation state here? -2 plus 4, -2, -2 plus 1 plus 1. Everything's good. Oxidation states are good. -2 plus 4 -2 plus 1 -2 plus 1. Everything's good. This is not a redox reaction. It shouldn't change. So the oxidation states didn't change, right? If the oxidation states change, then it's a redox reaction. If I form carbon monoxide, that would be a redox reaction, not an acid-base reaction.
Does it have to do something with hydrogens?
Hydrogens are good. +1 + 1. Got a duet. The same. The filled valence shell. So nobody can tell me what's wrong with this, so this must be okay. Because, you know, just because you're saying it doesn't look good, I'm not hearing any kind of justification for it doesn't look good. I need some kind of reason. And, I haven't heard any reason why this doesn't look good yet. It's not symmetric? Do things have to be symmetric? You're right, it doesn't look symmetric. I mean, it would sure be a lot prettier if it were symmetric. But is that a rule? The Lewis structures must be symmetric. If yes, then you're right, this doesn't look good. Maybe we can make it symmetric. Is that a rule that you guys used in Chem 4? Symmetry? No. Even number is better? Even number of what? Oh, even odd. Yeah. Even numbers are better than odd numbers. I know for nuclear theory. Have you heard the even odd? Yeah. Even number of protons and an even number of neutrons is better than an odd number of protons and an odd number of neutrons. That's an observation. It's a pattern that people have seen. And so maybe it's a pattern in nature, even, symmetry, that type of stuff. Actually, nature likes symmetry, but it doesn't have to be symmetric. And so the situation is, this is not stable. This Lewis structure is not stable. Why is it not stable? It's not stable not because of the octet. Octet's fine. Not because of the oxidation state. Oxidation states are fine.
Is it because of the electronegativity?
Well, electronegativity doesn't change. It's still the same. This oxygen wins. This oxygen wins. This oxygen wins. Winner takes all. Common bonding. Common bonding pattern. Common bonding pattern. What are the common bonding patterns? Oxygen. Have you ever seen this? You know what this is called?
Hydronium.
Hydronium. So that looks like this. There's been. Have you seen this? You know what this is? Acetate ion. Common bonding pattern. Common bonding pattern. I've seen this. And CO2. All these are common bonding patterns, right? There's nothing uncommon here. Each of these patterns has some kind of precedent in nature. And so, is there some other reason?
Lone pairs.
The lone pairs? Okay, what's the rule for the lone pairs? Is there a rule for the lone pairs? For example, here we have 1, 2, 3 lone pairs, but it's common. Here we have 1 lone pair. Here we have 2 lone pairs. All of these 3 are very, acetate's extremely common, hydronium's extremely common, CO2 is extremely common. And so is there a rule for lone pairs?
You can't have more than 3 lone pairs.
Well, are we exceeding? This is 3 lone pairs. This is 1 lone pair. This is 2 lone pairs. 1, 2, 3. All right, so now I'll tell you, this is why this is unstable. And you have to learn a new, maybe you already learned this. Have you learned the formal charge? Has anybody learned formal charge? The reason this is unstable is because of the formal charges. The formal charges aren't good. It can be made better. And what formal charge is the third way of counting electrons. You know 2 ways of counting electrons. When we have a Lewis structure, we can count the electrons using oxidation state. Oxidation state, sum it up in 1 sentence for me. What is oxidation state?
electrons it has and minus electrons it should have?
Yeah, that's one way. Oxidation state, the way we show that is by charge. The way we show how many electrons it has relative to what it shouldn't have is like a plus charge means it's short, the minus charge means it has extra, and the zero charge means it has the right amount. And so it's the charge on the atom, but how do we calculate that charge? We make sure when we count the electrons, we follow the simple rule. What is the simple rule? Not the octet rule. The simple rule is winner takes all. Winner takes all. When we do octet, does winner take all? When I'm counting the octet on the oxygen, does winner take all? It seems that way, but when I count the octet on carbon, it has an octet, right? And so I'm double counting. And so when we count octets, it's different. It's not winner takes all. When I count octets, it's how many electrons are around that. And so that's octet. How many electrons are around carbon? 2, 4, 6, 8. It doesn't mean carbon owns all of them. That's how many are around it. That's how we count octets, right? And so octets, these are little things you want. You know, if you don't like winner take all, you should come up with something that solidifies the concept of oxidation state in your mind. You know, something that you understand. Wow. All right, now comes the third way. The third way, some of you heard, some of you may not have heard. Let's see, who have I had? Actually, I have no one from Chem 4 in here. I talk about formal charge in Chem 4, and we really need to talk about formal charge in Chem 4 when you're dealing with Lewis structures, because this type of scenario happens all the time in Lewis structures. And so with formal charge, we count the electrons, but we follow a different philosophy when we count the electrons. And the philosophy is, rather than winner takes all, we're going to share. We're going to share. In other words, we're going to split it down the middle. 50-50 sharing. And so whatever way you can remember it, that's the way we're going to do. And so rather than winner take all here, when we look at the electrons and who owns them, we're going to do a 50-50 split no matter what the strength is. And so if we do a 50-50 split, that means this oxygen has how many electrons? 7. It's supposed to have 6, which give a negative formal charge. Formal charges are circled like this. Oxidation states are not circled. We can easily tell the difference. We never compare formal charge with oxidation state. Why?
They're very confusing.
Yeah, one, it's very confusing, and two, it would be meaningless. It's meaningless to compare formal charge with oxidation state. You have to compare formal charges with other formal charges or oxidation states with other oxidation states. In other words, you have to compare apples with apples and oranges with oranges. And those are just two different ways of looking at this. The formal charge on this carbon is, well, carbon ends up with 4. It's supposed to have 4. It's 0. The formal charge on this oxygen is 0. The formal charge on this oxygen is, with a 50-50 split, is 1, 2, 3, 4, 5. It's supposed to have 6. It's plus. And then the hydrogens are 0 and 0. And so this is formal charge. When we look at the formal charge, now we see why it's unstable. Why it's unstable is this oxygen gained an electron, this oxygen lost an electron. If you have a tug of war between two oxygens, who should win? The bottom left oxygen or the upper middle oxygen? Which oxygen should win? Neither. And so this is unstable. because one oxygen got an electron, the other lost an electron. So because of the formal charges, this is not a good structure. Unstable. And so being unstable is going to be kind of reactive. Now this is going to be an interesting reaction here that takes place, and that is, when we visualize molecules or ions or whatever, they're not static. Everything's dynamic at room temperature. And so what's happening is this molecule is vibrating, right? Rotating, translating. And so if we have something like this, there's free rotation about single bonds. So this whole thing up here is rotating around. And so I'm going to rotate it 180 this way. And so I'm going to point the hydrogen over here. I'm going to put the oxygen like this. This, of course, isn't drawn to very accurately. So it's all right. So imagine this. Imagine a vibration occurring here, such that, and when these molecules vibrate at room temperature, are they all vibrating at the same frequency, you think? Are they all, no. The same amplitude? No. And so what happens is, imagine this one has a very severe vibration which pushes this lone pair into the hydrogen. Well, that's too many electrons around hydrogen, and imagine if this electron pair gets knocked out, like this. What will result is this structure here. This is the correct structure for carbonic acid. It is symmetric. I didn't draw it symmetric, but it is symmetric. And so this is carbonic. So let's go ahead and write this out. What happens is CO2 plus water to a liquid, CO2 gas plus H2 a liquid, yields carbonic acid. What do you think about these collisions? Are these high probability collisions, do you think? High probability vibrations? You think this kind of vibration happens all the time here? No. And so it's not a significant reaction. In fact, this reaction is much more favored in the reverse, the decomposition of carbonic acid to yield CO2 and water. But nonetheless, what will happen is if you take a straw and start blowing into a glass of water, you're going to make that water acidic. You're going to make that water acidic because you're going to start generating a tiny bit of carbonic acid. Most of the CO2 will bubble out. It's not very soluble. But a little bit will react. This is the reason why our DI water is so acidic. Do you know what pH neutral is? It should be pH 7. Do you know what our DI water's pH is? 5.5, 5.4. That's pretty acidic. Is there somebody upstairs blowing with a straw into our DI water? Maybe, the chemistry gremlins up there, but it turns out, no. Our DI water sits in a storage tank up here in the ceiling, and the storage tank is open to air. And so the CO2 that naturally occurs in air gets absorbed into the water, and a little bit of it reacts with the water to form some carbonic acid, which lowers the pH of our water. And so if we want high purity water, this is why there's a distinction. A lot of people tell me, okay, I'm using distilled. Well, distilled water, you're going to expect the pH to be 7. For our DI water, I expect the pH to be about 5.5. And so this is not distilled water. If we want to get rid of the carbonic acid, do you know what we'll do? We'll take the DI water, throw it on a hot plate, and start boiling it. As we boil it, we're going to drive this reaction to the left. It normally goes to the left, but there's a tiny amount of residual carbonic in there. But we're going to drive it all the way to the left, drive off the CO2, make our water pH 7 again. And so that's called the boiled deionized water, which we're going to use in experiment 17. Get rid of any kind of CO2. You might have learned this in Chem 4. Non-metal oxides react with water to form oxyacids. Did you memorize that pattern in Chem 4? Yeah, so CO2 does this. That's a Lewis acid. SO2 does the same thing. SO2 will make sulfuric acid. SO3 makes sulfuric acid. NO2 makes nitric acid. And so all these are Lewis acids. We can react with Lewis-based water to form various acids in water. You may have also learned that metal oxides are bases. And so something like calcium oxide, this is a Lewis base. Calcium oxide is also a Bronsted base. You know oxide, right? Oxide is a moderate base or powerful base? He's oxide. Or weak base. Oxide is a powerful base. The only reason that calcium oxide is not a powerful base is because calcium oxide is not very, no. Well, it's not very reactive because it's a solid, no. There are lots of solids that you mix with water, you get a violent reaction. The reason why calcium oxide is not very reactive is because it is not soluble. If it were sodium oxide, you'd have a violent reaction. Solid sodium oxide. Because sodium oxide is soluble. But nonetheless, we could have a mild reaction here. In fact, this reaction is very favorable. And so if we take calcium oxide and mix it with H2O, what are we going to form? Yeah. Calcium hydroxide. And this is a highly favored reaction. And so we could take other oxides. A lot of oxides won't do this because they're so insoluble. The lattice is so stable. All right. So that's a little bit of Lewis. We're going to look at more Lewis acid-base reactions when we get to Lewis structures. So just a brief overview just to complete our discussion of chemical reactions. Now, I'm going to move on to chapter 6 next, which deals with gases. Gases are going to be pretty much the same as Chem 4. The only difference is, one, we'll talk more about pressure. Two, we're going to look at the ideal gas law in a little more detail. For example, does an ideal gas exist? Is there such thing as an ideal gas?
No.
No, it's just some kind of concept, right? There's no such thing as an ideal gas. And then why are we using the ideal gas law? There's no such thing as an ideal gas.
Because gases act like ideal gases at the temperature that we're used to.
Good. And so we got to understand, when do we expect large deviations from ideal gas behavior? When do we expect minimal or negligible deviations from ideal gas behavior? And so that's something we need to learn in Chem 1A. And then also mixtures, we're going to deal with mixtures and look at them from other perspectives, actually more complicated mixtures. And we'll look at the kinetic molecular theory in more detail. And so let me just briefly talk about gas pressures, or just pressure in general. When we think about pressure, there's going to be some kind of area. And pressure is just some kind of force per unit area. And one way I think about the force is, I think of it in terms of weight. Weight. And so normally when we think about weight, you can think about like swimming in a pool. Do you know what the world's deepest swimming pool is? The man-made swimming pool. Have you heard of it? It's new. It's in Italy, right? 131 feet deep. Swimming pool. And so, yeah, that, can you imagine the weight of all that water? If you go to the bottom of that swimming pool, can you imagine the weight of all that water? Can you imagine the pressure you must be under at the bottom? A lot, right? That's a huge weight. So, when I think about pressure, I normally think about the weight. And, you know, at sea level, the pressure is usually around 1 atm. And so I think about the blanket of air, and this blanket of air weighs about 1 atm. Well, 1 atm, we have other ways of expressing that.
724.
Yeah, 760 millimeters of mercury, liquid mercury. And so what this means is this: if I had a swimming pool and I filled it with liquid mercury and I submerged myself, about 760 millimeters is about 3/4 of a meter deep, then the weight of the mercury above me would be equivalent to the weight of this blanket of air above me. That's the way I imagine it. And so this is equivalent. The weight of this blanket of the air, 1 atmosphere, is equivalent to being 3/4 of a meter deep in a mercury swimming pool, or being how deep in a water swimming pool. Because mercury is a lot more dense than water. Right? Do you know the density of mercury? The density of mercury is, where is it? Here. What is the density of water? 1. And so that means mercury is 13.5 times more dense than water. And so, in other words, mercury weighs 13.5 times more than water. Well, if mercury weighs 13.5 times more, then what I need is 760 millimeters times 13.5, right, to get the millimeters of water. This is just a seat of the pants kind of calculation, no equation for this. But you see, I'm going to have 13.5 times more water. And so if I have about 1 meter here, then, you know, a 1 meter deep in a mercury swimming pool would be equivalent to 13.5 meters deep in a water swimming pool, because mercury is so dense. Does that make sense? And so what we want to do is we want to calculate the weight at the bottom of the world's deepest swimming pool. And so it's 131 feet deep. And so I have 131 feet of water. Let's assume it's at sea level. And so if I'm down here at the bottom of this, then I got 131 feet of water plus 760 millimeters of mercury, liquid mercury, worth of atmosphere weight. And so what I want to figure out is how many atmospheres is it going to be at the bottom of this. And so we're out of time, so we'll have to finish this calculation next time.